Hello and welcome to another orbital mechanics video. We are still working through the problems in the book Orbital Mechanics for Engineering Students by Howard D. Curtis. We're up to problem 1.15 and this problem is asking us to figure out on our plumb bob at the end of a 30-meter string that is stationary on Earth, how far would that plumb bob angle out or deviate out from its vertical due to the rotation of the Earth. And it's at a latitude of 29 degrees north. So this one's a little bit simpler than the last one because it doesn't have the object is not moving relative to the rotation of the Earth. So we can use an equation that is provided as a simplification in the book. And that equation is V equals W times the radius from the center of the Earth times cos times the cos of the angle to the north. However, we can also derive this quite simply from looking at the Earth and the angle. We know that velocity equals angular velocity times radius. And we know that this globe is spinning on its vertical axis. Well, it's not on its vertical axis, but for our purposes it is, because we're assuming that it's spinning that way around. So this distance here is our radius from the center. So we just have to get that value there, which is r cos phi, or 29 in this case. And so angular velocity times that distance equals our velocity. And we can also quite easily get the acceleration from this because we can differentiate this. And when we differentiate that, we get WR cos phi, the derivative of our I plus derivative of phi, minus derivative phi, angular velocity r sine phi I. But we actually know the derivative of phi in this is 0 because it's constant. So that all becomes 0. We don't need that. And we're just left with angular velocity r cos phi times the derivative of our I axis. And we know from previous videos that that is the same as the angular velocity cross product with the I axis. And we also know, and you can look at this in the book and think about it yourself until you're happy with it, that the angular velocity vector equals the angular velocity cos phi j plus the angular velocity sine phi k. Now in the book, this is actually another letter that they've substituted in, but because we know that there is no movement of this particle or this plumb bob, and we know that it's rotating around the vertical axis, not kind of worrying about the angle of the Earth because we're doing it relative to the Earth, we can say that this angular velocity is that in the book they use this symbol here, which is the rate of change of the rotation, but we know we're just rotating around the axis normally, so that's just angular velocity. Now in the book it actually comes out with when you do it through, you get this value, and that's correct. But in the book, it actually loses a negative sign in its final simplification. I've worked it out a bunch of times, and when you actually do it out, you get a negative here. Now this negative is missing in the book. You actually get the wrong answer. It ends up going north. The plumb bob goes north when we know from tides that the rotation of the Earth causes the tides to balloon outwards. The water doesn't go to the north and south, it balloons outwards. So if we're at 29 degrees north, the rotation of the Earth is going to kick us this way towards the equator. So we know that it is going to send us south, but when you use the equation provided by the book, it actually goes north. So they've dropped this negative in their calculations, but the negative should be there. And when you plug your values into the acceleration equation, we have the angular velocity from the simple equation for the angular velocity of the Earth, which is 2 times pi divided by 86,160. All of this is in the MATLAB description below, so you can just look there. And we know phi is 29. We know the radius of the Earth. This plumb bob, we assume, is just sitting on next to the Earth's crust, right? So when we plug that in, and it's done in MATLAB, you get minus 0.01438J minus 0.02595K. And this is going south, and this is going this is the acceleration, the centripetal acceleration. Now, actually, we did the centripetal acceleration in the last one, but I didn't really talk about it very much. I just kind of said it was, coming off the gravity. But if you think about if there was no air resistance and you're traveling around the globe, if you at a certain speed, you will start to take off, right? So as your speed increases, the force that is pressing on you from the Earth is decreasing. So we know that this centripetal force is actually it's coming off the force of gravity, even though the acceleration is acting towards the center of the Earth. That's just the nature of how you move around a globe when you're falling into it. But the actual force itself that you're feeling against the ground is reducing because you're going faster. You're gradually taking off. So this force here, as we see, when you're comparing it to gravity, you're taking it off the gravity, even though this is technically in the same direction as gravity. So we're just going to move on and we're going to work out the values that are going on here. We know the acceleration of this particle now. This is the acceleration, and that is the velocity. So just turn over, and here we have the it drawn out again. Now F equals ma, that's always, and we have our southerly acceleration, and we have our acceleration along the vertical, and we've just pointed that down because that's the directional value for it. Well, it's actually negative, but we're just going to say it's down for simplicity. So we're going to take that off gravity here, right? So the acceleration due to gravity less the acceleration due to the curvature of the Earth, the rotation of the Earth, we're going to get a ratio. So this ratio between this and this, when we include gravity, that's just a negative 9.81 there. The ratio between that is 0.00147. That's tanθ, as we know, opposite over hypotenuse. You can work this out bits and pieces yourself, but that's the ratio. And then when we take the 30 meters here, we have tanθ. We can get this distance here again, opposite over adjacent. I think I said hypotenuse a second ago, but yeah, opposite over adjacent, and it's the same here. This is your opposite and adjacent. So tanθ equals d over 30, and when you multiply that 30 by tanθ, you get 44.1 millimeters. And that's what the answer in the book gives. And it's also pulling it south, though. If you use the equations provided by the book, you'll get north. So I'm pretty sure that's a typo in the book. Let's see if they use that again. Yeah, I hope that was clear. If you have any questions, leave them in the comments. There's multiple ways to derive these equations. The one given in the book is massive and complicated, and then you simplify at the end by replacing the variables that are actually zero. But there's other ways to get to these equations, and I think it's good practice to try to derive these equations through other means. Yeah, nothing else to say there. Thank you very much. Goodbye.